Welcome to this presentation on my doctoral research and thesis titled Solving Optimization Problems via Maximum Satisfiability, Encodings and Re-Encodings. I'd like to first thank the ACP for giving me the Doctoral Research Award. It's a very great and unexpected honor and one that I'm very grateful for. First, a few words about myself. I have a master's degree in mathematics, and I obtained my doctorate from the University of Helsinki in June of 2018 under the supervision of Professor Matti Järvisalo. Nowadays, I'm working as a postdoc at the same university. So here's the one-sentence summary of today's topic, my doctoral research. During my time as a PhD student, I worked on developing maximum satisfiability, or MaxSAT for short, focusing especially on solving real-world optimization problems. And more specifically, I worked on understanding and developing solver-independent preprocessing for MaxSAT and on applying MaxSAT for solving NP-hard data analysis problems in practice. And the rest of this talk is divided in two parts. First, I'll speak some more about MaxSAT and its role in modern optimization, and then I'll briefly overview the main results of my doctoral research. So MaxSAT is an exact Boolean optimization paradigm based on propositional logic, which means that we're working with binary variables and clauses and trying to find assignments that satisfy as many clauses as possible. Modern MaxSAT builds on the success of SAT and SAT solvers and is today finding an expanding range of real-world applications where it often provides an effective and orthogonal alternative to some other constraint optimization paradigms such as MIP and finite domain constraint optimization. And here are some examples of the domains in which MaxSAT is being applied today. As I mentioned, the list is increasing. For the last two MaxSAT evaluations, we had benchmarks submitted from 17 new domains. And central for this increasing number of successful applications are the advances in solver technology that we're also seeing. Over the last 10 years, we've seen a continuous improvement in solver technology, which is exemplified by the plot here, which demonstrates the number of instances solved by the winners of the last 10 MaxSAT evaluations when run on this year's evaluation benchmarks. Here we have the number of instances on the y-axis and the different timeouts on the x-axis, so you want to be as high up as possible. And we can clearly see that starting from the winner in 2010, which was able to solve around 200 instances, and ending with the winner this year, which was able to solve over 400, every year the winner of that year is able to solve more instances than the winners of previous years. And this year, we could solve 83% more instances than 10 years ago. So the take-home message from the first part of the talk is that MaxSAT is a fairly active area of research with new improvements to solver technology and new applications being proposed every year. And among the different algorithms for solving MaxSAT that have been proposed, the so-called SAT-based MaxSAT algorithms and solvers are central for my thesis and also the applications that I mentioned. By SAT-based MaxSAT algorithms, I mean solvers that make iterative use of SAT solvers. There are a few different ways you can do this. There are successful solvers that do upper bounding search, lower bounding search, and even combined SAT solvers and IP solvers. The details of these algorithms are not important for my presentation, but I'll say here that the central results of my doctoral research are applicable to all of these three types. So moving on to discussing my thesis research, the core thesis summarizes 6 publications that aim to improve MaxSAT-based solution methods to hard combinatorial optimization problems. These publications are further divided into 2 parts. The first part deals with MaxSAT solving techniques and specifically preprocessing, and the second part focuses on developing new MaxSAT-based solution methods to solving hard data analysis problems. And I'll first briefly overview my work on preprocessing. By preprocessing, I mean the application of different kinds of simplification and deduction rules to an instance prior to search with the hope of making that instance easier for a solver to solve. For this presentation, I'd like to discuss 2 of the main results for preprocessing that we got during my thesis work. The first one deals with how to use preprocessing in practice. We show that for MaxSAT, the integration between the preprocessor and the solver needs to be done carefully because otherwise it's fairly easy to end up degrading the overall performance. This is shown on the plot here, where the number of instances is on the x-axis and the timeouts are on the y-axis, so you want to be as far to the right as possible. The blue line is a basic MaxSAT algorithm that does not use preprocessing, and the green line corresponds to adding preprocessing in a black box manner to that solver. So we see that that loses you about 10 instances. We also demonstrate that by being a bit more clever, you can unlock more of the potential of preprocessing and get performance equivalent to the yellow line over here. So you win around 20 instances. The second main result on preprocessing that I want to discuss here is more theoretical. We show that many of the commonly used preprocessing rules for MaxSAT have a very limited effect on the MaxSAT algorithms and solvers themselves. More specifically, we established that the inability of those rules of affecting small unsatisfiable subsets of constraints, or MUSs, is a fundamental limit on how much they can affect MaxSAT solvers and MaxSAT algorithms. And since these papers and my thesis, the role of preprocessing in MaxSAT solving has been increasing steadily. We see more and more solvers that make use of preprocessing when competing in evaluations, and we also have more general proofs of correctness covering essentially all of the preprocessing rules used in SAT solving, also for MaxSAT. Now I'll move on to the second part of my thesis. This part contributes to the recent trend of using constraint optimization for solving hard data analysis problems. We develop a MaxSAT-based solution method for two such problems, the correlation clustering problem and the bounded Treewidth Bayesian network structure learning problem. So in correlation clustering, we're given a set of data and a pairwise similarity measure over the data points. This can be expressed as a graph like this, where the data points are the nodes and the edges between 2 points are labeled with a plus if the 2 points are similar, or with a minus if they're not. And now we would like to compute a clustering that matches this measure as well as possible. So intuitively speaking, we would like to see similar points being assigned to the same cluster and not similar points being assigned to different ones. Here's an example where we're able to follow all of these similarity measures except for the one over here. And what's important to note here is that the number of clusters is not given as input, and instead it needs to be learned during search. This makes correlation clustering especially well suited for domains where you might not know how many clusters your data has. And indeed, correlation clustering has found applications in many different domains, including the ones I've mentioned here. In my thesis, we develop a MaxSAT-based solution method for correlation clustering and empirically compare it to other proposed solution methods. Here's an example of one of the main results that we got. This plot shows the results of an experiment where we took one instance, so one graph, and then we randomly selected a fraction p of the edges in that graph, ran our clustering algorithm only on those edges, but computed the cost of the obtained clustering with respect to all of the edges. Here we compare the MaxSAT-based method to two approximative algorithms that were specifically designed for this kind of data, and we see that MaxSAT is able to obtain clusterings of significantly lower cost, even for very sparse data sets. An added benefit here is that whenever you throw out edges, you make the MaxSAT-based solution method faster. So we can obtain better scalability without sacrificing too much of the solution quality. So the second focus problem of my thesis is the so-called bounded Treewidth Bayesian network structure learning problem. Bayesian networks are a very commonly used probabilistic model that compactly represent the joint distribution of a set of random variables. And in the so-called score-based setting for learning Bayesian networks that we're working in, we start with a set of observations over some random variables or data, and then want to learn a Bayesian network structure or a directed acyclic graph that in a certain sense explains this data as well as possible. And this is a very well-known NP-hard optimization problem. And the motivation for our work comes from a very typical use case of Bayesian networks. Once we've learned a structure like this, we often then want to use it for probabilistic inference, that is, queries like these. And over general network structures, also this inference is NP-hard. However, it becomes tractable whenever the network has bounded Treewidth. Treewidth is a well-known graph theoretic measure that has connections to tractability in many domains. The fact that probabilistic inference is tractable with bounded treewidth is analogous to how bucket elimination is tractable for constraint programs whenever the underlying graph has a bounded treewidth. So in this paper, we're trying to learn network structures that not only explain data well, but also have a bounded or low treewidth. Here it should be mentioned that bounding the treewidth of the network structure to be learned is a highly non-trivial addition to the problem. Bounded treewidth Bayesian network structure learning is NP hard, and even checking if a graph has a bounded treewidth is known to be NP complete. So in my thesis, we develop a MaxSAT-based solution method for this problem and compare it to some other exact approaches, namely two that are based on integer programming and custom cutting planes, and one that is based on dynamic programming. Here we have a plot again with the instances solved on the x-axis and timeouts on the y-axis, and we see that MaxSAT scales better than any of these other exact approaches. And interestingly, we also found that the highly non-trivial treewidth constraint was actually fairly central in making MaxSAT work. And without it, the MaxSAT encoding for learning Bayesian network structures did not work nearly as well. Before concluding, I'd also like to mention that in addition to the 6 core publications of my thesis, my doctoral research resulted in 7 related papers that develop MaxSAT algorithms and applications. I also contributed to some open source software, namely MaxSAT solvers and preprocessors, and produced some openly available benchmark sets that have been used in the evaluations since 2015. My more recent work builds on these publications. Here I'd like to especially highlight my work on hybrid algorithms for MaxSAT, where we try to combine several existing algorithms in non-trivial ways in order to gain performance over each individual component. This resulted in one of the best incomplete solvers in the recent evaluations, as well as one of the best complete solvers and the best paper award at this year's SAT conference. So to conclude, the take-home message of my presentation is that modern MaxSAT has in the recent years developed into an effective and competitive approach to exact optimization, and that my thesis research has played a small part in this development. Even so, there's still much work to do. Here I'd like to mention 3 future research directions that I think are both promising and very interesting. The first is to push the research on hybrid search methods further. One example here could be to try to develop some kind of in-processing for MaxSAT. In-processing refers to interleaving pre-processing and search. This is widely used in SAT solving already, but currently not as much in MaxSAT. The second interesting research direction would be to build the understanding of and support for incremental applications of solvers. Building MaxSAT algorithms and solvers that are easy to use incrementally would in turn allow such solvers to be applied for solving even larger encodings and settings where we want to solve many instances that are closely related to each other. And finally, I'm also very interested in improving the understanding of the relationship between different applications and different optimization paradigms that exists. Empirically, we've seen that the performance of a specific optimization paradigm, such as MaxSAT or MIP, depends very much on the domain in which it's being applied, but a formal understanding of which paradigm I should choose for solving a specific problem remains to be developed and would, in my opinion, be very important for the field on the whole. So once again, I would like to express my sincerest gratitude towards the ACP for the award and my supervisor Matti Järvisalo, without whom this research could not have been made. I would also like to thank all of the other people involved in my nomination, as well as all of my co-authors and collaborators, and all of you for watching. I look forward to seeing you in the session where I'm happy to take any questions that you might have. Thank you very much.